All right, let's do this. So this is, I think this is our last lecture. We'll meet next week, which will be a wrap up, typically shorter, but we'll go over some stuff. So somebody asked about the final exam. It was scheduled to become available next Wednesday at around this time, but I think we'll make it available on Sunday, the 4th. It'll have the same due date, so that'll give you a full week to work on it. Although you shouldn't spend more than an hour or two on it. So just, in terms of scheduling, we'll send a message on Slack. I'll do that I try not to use the everyone tag too often, but I'll do that just to say that it's available for sure.
And we can continue just like with the midterm. You can leave off and then log back in. And
this one's a little bit different. So it's not. So you'll go to Blackboard. You're going to download a PDF which has the final exam questions, and then there's an R Markdown file for you to do your answers on this one. So it's a little bit more like a lab than what the midterm was. So then you'll upload your PDF of the final exam questions. So hopefully you could take a look at it, and then if you have questions about anything like that, we could deal with it next Wednesday, or you can email us in the meantime. Other questions?
So the exam, we're going to download the PDF, which is the questions. We'll do the same way we did the labs, just knit to PDF and then upload.
That's exactly right.
Okay.
So there's you're going to work with the sort of a small data set, and the data set's kind of embedded in an R Markdown file that you'll put your answers in. So you have a PDF that has the questions, and then essentially the R Markdown file becomes your answer sheet. You can think of it that way. Yeah. So you'll be able to just run. Well, I'm sorry, go ahead, Alex.
The data is going to be in the package, whatever.
Yep.
Whatever package will be the R Markdown. Okay.
Yeah, it's actually just a long R command. The data is literally embedded as like just reading it inline. So we find it easier. So it's just like a little toy data set for you to play around with.
And the final is due when?
The 11th, midnight.
11th. Okay, thank you.
Yeah. So it's a little bit there's what, a few multiple choice, a couple of short answers, and then, like I said, a data set that you'll work with.
Thank you.
Yeah, trying to make this one a little bit more authentic than just a multiple choice test, but it's sort of, from our point of view, it's like, at least my point of view, I should say, it's like I'm not usually a huge fan of these, exams like this, but this one I feel is a little bit closer to what you might be doing. And it's sort of a sanity check that you have the key concepts. I mean, that's kind of what we're looking for. And in a lot of ways, we want all of you to do really well, because it means we did okay with the course design. So.
Sorry, Professor, last question. And how many questions are there going to be?
Here, I just opened it up. So there are, there's 10 multiple choice, and then there's a data set you're going to analyze. And so there's probably, I'm trying to count here. I got to scroll through the data. So 1, 2, 3, 4, 5, 6, 7, 8 questions, 6 of which are sort of calculation things, and then 2 that are sort of interpretation things.
Thank you.
What's the question in there? When is, okay. Yeah, sometime Sunday. It's not uploaded to Blackboard yet, so you just need to set that up. All right, so this is actually from, just to point out, this is from the logistic regression slide deck that we didn't actually get to these set of slides. So spend a few minutes talking about predictive modeling. So, and this is, I'm trying to shift from sort of the way we introduced regression in terms of what I would call inference, right? We're looking at how some variables are related to other variables. So we have independent, dependent variables, and we use the word predict, right, in that context, and that we could predict outcomes, and we use the predicted values minus the observed values to get residuals. So we use that in a lot of ways, but so I would say for the last century or so, that's kind of what statistics is largely been used for, is to try to understand how these variables are related to some other variables. Now, with the sort of proliferation of computers and high-powered computers and, businesses, these statistical models have kind of shifted in how they're used in order to try to predict outcomes for new data. That's sort of a relatively new concept, right? I think, and using it that way. And that's kind of what data science is to me. I mean, sometimes I argue that data science is just statistics, or maybe it's like applied statistics, right? Statistics is like applied mathematics, and then, right. And so in data science, oftentimes we're just trying to, make predictions to make decisions about a business or about, in our, Angela and I, we're using predictions to try to identify students at risk so we can provide, specific interventions to help them be successful. So there's a lot of different ways that this can be used. But when we go to this predictive modeling, how we're going to evaluate models is going to change a little bit. So that's kind of what I want to introduce. Right. So this is sort of the basic from as a carryover from the logistic regression. If we're thinking about it in terms of predicting a dichotomized outcome, right, we're going to look at the log odds, right, and then we can calculate and convert that to a probability by taking sort of the exponent of it, right? And so, in this case, right, what happens? If you remember, we were looking at this prediction of the likelihood of passing given a number of hours studying, and so if somebody didn't study at all, we might say they have like a 1.6% chance of passing, right? That's not something we observe. It's just a new student that comes in, and we might want to do that. And then we can, of course, 4 hours, right? So these are just inputs to these functions. And so we could look at, the fitted values. Now, when we get to model performance, at least this part of this table should look very familiar, right? We talked about type 1, type 2 errors in terms of making, in the context of null hypothesis testing. Well, it turns out that framework applies for doing predictive models, right? So think about a situation where, we design this model and then we have new, whatever coming in, and we're going to make predictions. And we want to evaluate the quality of those predictions eventually, right? We'll observe an outcome. So let's actually use what Angela and I work on. So we try to predict student success. So right now we're running a study where we have the, DAX we give to students and provide some interventions, or we're going to use DAX data to predict whether or not a student's going to pass their first semester. So it's they pass or don't pass, okay? And so we have a few years of data, we built these models, we predict it. And so, we could say this past summer, we predicted students coming in fall 2022, whether or not they're going to succeed or not. Now that the semester's coming to an end, we're actually going to observe that outcome, right? And so we could say, well, how good were our predictions? And a couple of scenarios could happen, right? We could have predicted success and we actually observed success, right? So that's great. That's what we want. We could predict failure and actually observe failure. Well, in this case, we don't really want students to fail, but from a model perspective, right, that's good, right? We accurately predicted that, right? And so we could predict success and actually see failure. And that would be our type 1 error. And this is a type 1 error from a model point of view. And we could have the opposite where we predicted a failure but saw success, right? And this is used a lot, right? Let's take marketing, for example, right? So, marketers often just want to predict whether or not an ad is going to have a good impression, right? Somebody's going to click on the ad. And so, have those things. So Facebook is kind of, they have a whole giant, they have a data science building, right, of people trying to figure out how to, maximize engagement. So that's sort of the framework, but then that's going to fall into having some different metrics that we're going to want, right? So we have, we could talk about it in terms, of specificity, right? So that's the case where we have the predict negative outcome and see a negative outcome. And then we have sensitivity, right? So oftentimes we're looking at these things in conjunction. And then we could also have false positive, false negative rates. But this is all kind of oriented to this sort of classic type 1, type 2 error rate framework. So we'll dig into this a little bit more. But this is going to be this bit right here is going to be one of our key metrics. And we're going to call that a confusion matrix. And I'll explain that in a second. So here, I'm going to look at a data set here. It's up on the course website, where we're going to try to predict heart attacks, right? And so we have 294 observations of 11 variables, and num here, right? If it's 0, let me see if I remember this. So 0 is less than a 50% diameter narrowing, and 1 is a greater than, right? So this is sort of an outcome or an indicator of heart disease. So we're predicting technically heart disease here. And we're going to predict this from all of these other variables. Okay. So the first thing that we typically want to do is just look at a simple contingency table. So in our heart data set, right, 261 are true, meaning they had more than 50% narrowing, or they have an indication of heart disease, and 33% did not. Right. And so what we want to do is try to predict that. Now, I just leaving this in here, this is sort of beyond the scope of this class. There were a few missing values, so I just went ahead and imputed it using a package called mice. So if you have missing data and you want to do that, you can kind of replicate this. I should say, I could say a whole lot about this. I'm only doing one imputation here, where technically you should do at least 5 and look at the multiple results. But as a quick and dirty way to do it, I'm going to do that. And from the complete, I now have a data set with no missing values. I only show this that you should look at this. If you have to deal with missing data, mice is almost always what I use. It's much, much better than either dropping the missing values or doing a mean or median imputation. There's kind of other processes, but this one's pretty robust. All right, so let's do, let's set up our data. So if we're trying to evaluate our models in terms of prediction, we're kind of going to move away from things like R-squared, which is what we used for regression models and other things. And instead, what we're going to first do is split our data into 2 pieces. Because what we want to do is train or develop a model with what we call a training set, and then check its accuracy with some validation set. And we want to keep them separate, because if we just use the same data set to both train and validate, we are very likely going to end up overfitting our data to that data set, which means it's going to be less effective for future predictions. So there are lots of ways to do this. As you go through the program, you'll learn to do this in Python. You'll learn to do this in R. If you're going to do this in R, there's used to be Caret was kind of the go-to package to do this stuff, but now Tidy Models, I think, is reached a level of maturity. And if you're, hopefully in January, I think Angela and I are going to give a talk with some students that we did an independent study this semester with, that looked at benchmarking predictive models. So we'll probably have a lot more to say about that there, where we're looking at, I don't know, I think we have almost like 300 different predictive models, like hopefully over 100 different data sets to kind of look at their relative performance. So we'll do a talk probably late January, early February on that, and there'll be an announcement, so look for that. But Tidy Models is sort of now the go-to approach that simplifies this. But this is just using base R, where I'm going to just take, so I'm taking 70%. I'm going to use 70% for training. So I just call it heart train. And then the remaining 30% will be my testing set or validation set. Okay. So now looking, I want to first look at the proportion of, in my training set. So, matches what we had over here, which we had 33. So we're looking at 33% had ones and 66%. Now I want to take a moment, right? So when we're comparing or evaluating our prediction model with a 0-1 outcome, a dichotomized outcome, we're not looking at how better than 50-50. What we need to do is look at sort of the larger of the proportion, right? And I call this the guessing rate. So the simplest model I could define here is that everyone doesn't have heart disease. And that's my model, everything is going to be 0. And if I put that model into practice, I would be correct 66% of the time, right? So what we're looking for is accuracies that get larger than 66%. And we'll come back to that in a few minutes. So what do we do, right? So nothing new here. I'm just running a logistic regression, but note my data set here is just a training set. We could look at the regression output, but really we can look at the predicted value. So here I'm getting the predicted value from my training. I'm still looking at just the training set, my test set, validation set aside, right? And this is great. So I could see the distribution for the false outcomes is kind of skewed to the left, where my true is skewed to the right. So that's great. There's nice little separation here. So this is kind of a nice little diagnostic to look at. Now, I need to dichotomize out my outcome, and we'll get back to this moment. For now, what I'm going to do is say if the prediction's greater than 0.5, I'm going to call it, that I'm going to predict they have heart disease. If it's less than 0.5, I'm going to say they don't. Right. And now I'm going to run. So I'm still working with my training set. So I'm looking at that predicted class that I had, right, by the actual outcome. So this is what's actually observed. And I'm printing this out. So what we have here, right, this is the basis of how we're going to evaluate our models. This is called a confusion matrix. So what we have here is this row are individuals that we predicted no heart disease. And these are, this row represents individuals that we predicted heart disease. This column represents individuals who did not have heart disease. And this column is individuals that do. So this cell represents, we predicted no heart disease and they did not have heart disease. So about 61.5% of individuals, we predicted no heart disease and they didn't have heart disease. And in this cell, right, we predicted 24.8% of individuals would have heart disease and they actually did. So then this cell, which is where we predicted no heart disease, but they actually did, and this cell where we predicted heart disease, but they didn't, is our error, right? This is where things went wrong. So if we sum this cell and this cell, right, that's our accuracy for the model, which in this case turns out to be 86.34%. So if you remember, right, 66% is what the baseline is, right? If I just looked at right here, where I did no modeling. So our model in this case is 20% better than guessing, right? And that's pretty good. That's pretty good. But there's some problems, right? This is all with the same data set. So really what we want to do is look at, so if we look at our, our test set, it's a little bit different. We're at 58%, right? Just because of random chance of how I split the data set. But now what I'm going to do is run my prediction. And what's key here is I have this new data parameter. So I'm sending in my test set and getting a prediction. And of course, I have to split it because this is going to give me a predicted probability. So I need to say, well, yes or no. I'm going to make my cut point at 0.5. And then I'm just going to create a contingency table. And so here I had 56% predicted no heart disease. They didn't. 25.8 predicted heart disease and they did, right? So I had 82% is the accuracy of my model, which in this case is 23.6% better than what it is in the test set. And when you're doing predictive modeling, this is what you actually report, the outcome from your test set. Now this is kind of an unusual example. And if I rebuild the slide deck, it'll be slightly differently as I split that validation test set. Typically, the validation set accuracy is not going to be better than the training set, but this is a data set that is actually pretty good at prediction, and not all of them are like that. How are we doing? So far, so good? Okay, so that to me this is where I always start, and this is often where I make a lot of my decisions, looking at these confusion matrices. But there's a few other approaches you can do. There's something called a receiver operator characteristic curve, where we're going to plot the true positive rate, also the sensitivity. So if we go back to this chart, right, we're looking at sensitivity. So we want to plot that against the false positive rate, or the probability of false alarm at varying thresholds. So essentially what we're going to do, right? So here I set my threshold at 0.5. But what we're going to do is say, well, let's try 0.01, 0.02, 0.03. We can go all the way up to 1, right? And in this case, right, so there's a calculate rock. So this is actually a function I wrote. So if we go to, I just want to show you where this is in case you want to use it and adapt it. There are built-in resources, but I had, specific desires for what was the name of the file? Calculate rock. Here it is. So it's in this rock.r. Let me throw this link in the chat in case you want to get it, but it's all on the GitHub. And next week I'll explain how you can get all the resources, which was also adapted from someone else. So I just took someone else's to do this. And so we get an area under the curve of 0.918. And what does that look like? Well, here's the plot. So what we're doing, right? So we're trying different thresholds, right? And so if the line was exactly on this blue line, this is sort of the guessing line. This means that there's no advantage, right? So the false positive rate is equal to the true positive rate, means that the model is not contributing any additional information. So when you're looking at rock curves, what we really want is the lift. In a perfect model with perfect separation would go straight up to 1 and then straight across. So the area under the curve is the or what we say with the rock, or AUC, is the area under this black line. Okay, this is also really useful in that it helps us determine where the cut point, the most optimal cut point. So what we're looking for is where, if we could draw a line perpendicular to this blue line or the unit line, that's where we're going to want to do it. So on the right is a cost curve. Let me go to the accuracy curve because I think this is a little bit easier to understand. So what we're doing here is we're going from left to right, changing different thresholds and calculating the false positive rate and the true positive rate, and then getting an accuracy. So over here, right, you could see as we increase the threshold and we get close to 0.5, which is what I used, right? But the optimal accuracy would occur if we had a threshold of 0.46. So if we split the yes, no, or 0, 1 at 0.46, that's where we could optimize it. But we could see it's pretty flat in the middle here. But this could be a problem with imbalanced data, and we'll see that in a minute, right? But anyways, you'll see this area under the curve. I'll be honest, it's I don't think it's the best metric to evaluate models, but it's been used for so long, people still report it. So you'll see it, and you'll encounter it more in the program. All right, so let's talk quickly about caution on the interpretation of accuracy, right? I cannot emphasize enough how much you need to look at what the base accuracy was. And the example I'm going to use, it's a little dated now, but in 2016, some researchers from Facebook, it was Facebook, now Meta, had published a paper on their ability to predict sexual orientation. So and they use something called support vector machines. Actually, they used a couple things: logistic regression, random forests. And this guy actually got some news, if you're paying attention, I guess 7 years ago now, that they were able to predict sexual orientation with 90% accuracy, which sounds fantastic, right? However, I went looking around, I go, geez, that seems interesting. But Gallup in 2018, so 2 years later, so this is as close as I could find poll data, estimated that about 4.5% of the American population identifies as LGBT. I should update this Q+, but that's what they called it in 2018, right? So more than 95% of the population in 2018, at least according to Gallup, identified as heterosexual, right? So I go to Facebook and say, I have a better model. I'm just going to predict everybody's heterosexual, and I'm going to be correct 95.5%, 5.5% better than your model, right? So this is why you need to be really, really careful with these things and not overstate the accuracy of your models, and how well they can, predict things. And really, if you're getting into this, be very, very wary or concerned if you need to predict rare events. And what do I mean by rare? So if you look at the proportion of true, false, 0, 1, however you code your outcome, right? When you get to a place where it's like 90%, 10%, 95, 5, quite frankly, you get, where you have one class that's more than 70% of the total, models are going to have a really, really hard time, unless you have really good measurements or good variables, that are correlated to your outcome. So rare events are really, really hard to model. So, and we can actually see this. So this is something that it came up for me in a different context before I was even thought I would end up in a data science program. When I was working on my dissertation in educational psychology, and I'll talk a little bit, I use logistic regression a lot to try to predict, treatment, whether or not people decide to take a treatment or not, in sort of observational studies. And this is a sort of a step towards quasi-experimental designs. But in my dissertation work, I was looking at charter schools versus traditional public schools. And this is one of those situations where it's a rare event. In the United States, about 3% of students go to a charter school. So I'm trying to predict, from these fairly large data sets, right? What turns out to be a rare event. And when I was doing the logistic regression and I'm looking at the predicted values, there were some oddities going on, and I needed to understand that. So I ended up writing a little simulation more than 10 years ago to kind of look at this. So I'm just going to go to the plot. I'm not going to worry a whole lot about the implementation, but this is using logistic regression. So what I did is I set up a data set where a simulated data set where I'm trying to predict, true, false, right? So true on the right, false on the left. And what this plot represents is what I did is I simulated the data set so I had the same number of true and false. And so the only thing that I did as I went down is now in this plot, or okay, wait, let me explain what this is. So the red here is the distribution for false, and teal is the distribution for true. This is kind of analogous to this plot that I showed earlier, where we looked at the predicted values of no heart disease, and these are the predicted values from heart disease. So I had here, and I did this a bunch of different ways. So I had moderate separation, probably pretty common in what you would see in a data set with a single predictor. So for each of these, I had 1-to-1, and each of these dots represents the minimum of the range of predicted values. And these dots here are the maximum, right? And I think there might be 20 random samples for each of them. So this bar represents the range of the predicted values, right? Which is good, right? It spans almost the entire range. So when I go up here, what I did is now I have twice as many zeros or falses as trues. Everything else is constructed the same, but my sample size is such that I have 2-to-1, 3-to-1, 4-to-1, all the way to 10-to-1, right? So this would be a situation where 90% of my observations are zeros and 10% are ones, and I'm trying to run the same model. So everything else held equal, the range of predicted values is going to shrink, right? And you should be aware of this. This is going to be true of logistic regression and in almost all contexts, right? When you have rare events, that range of values is going to shrink no matter what. And that also has implications in terms of interpretation of those predicted values, right? So we want to think about predictive probabilities, but when you have rare events, you can never have really large predictive probabilities. And so there's all sorts of implications here that you need to think about. All right, so and then on this slide, there's a whole bunch of additional resources, mostly on logistic regression, some videos that might be of interest. So questions about sort of a crash course to predictive modeling. I like to do this to set you up for the rest of the program. You're going to dig into these concepts in a lot more detail in many of the courses, but I'll answer some questions about that before we go to Bayesian.
I guess a simple one would be how do predictive failure models work then?
I'm not sure if I'm familiar with that term, but just decoding the sentence, it would just be you're trying to predict, failure. If you're trying to predict failure, you're
Sorry,
just kind of reversing the question.
Yeah, I guess that was kind of like the next question that I was going to go down, is that like normally I've seen them used for how do you detect when a motor is going to fail in a CNC mill, for example, based upon a series of sensor suites.
Okay, so you could do it the same way. You would just encode, you might just encode the failure as 1, right? So it has to do with how you label the outcomes. But the key is that there's only 2 outcomes, right? That you're going to use for a classification problem.
Okay.
Right. So, I mean, even in the heart disease example I just showed, right? I guess you would want to predict, you're trying to predict who has heart disease, so you give them, specific treatments. But yeah, I guess in cars you want to predict, engine failure, so you can fix it before that happens. So I think it just has to do with how you label it.
Okay.
I have a quick question. So I
Sure.
guess in general, one takeaway based off of like your commentary would be like, is regression somewhat limited with an unbalanced data set? And you should kind of take caution in terms of if you have an infrequent case, regression is probably not your best solution.
No, I mean, I would be a little bit more broad. If you have imbalanced data, almost any predictive modeling or procedure you're going to use, regression or otherwise, is going to have a hard time.
But aren't there specific model? I don't know what they are, but aren't there specific models designed for that? Like, for example, we talked about in 607, like for fraud detection, some of it is like synthetic data, or it's like, I guess maybe an unsupervised technique or some type of like graph network modeling.
Yeah, there are there are some procedures I think are better. I'd have to go. Oh, we just saw tonight, Angela, didn't Cliff say like supervised vector machines were good for, so there are some that are going to be better. And actually that would be a great question if you come to the talk in January. Might be able to give you a little bit more answer, because we're trying to look at this from a sort of very macro point of view to try to understand which models are good for what data sets. So I don't really have a great answer for you right now, but where I'm exploring it.
Okay, but at
if
least
you do some
when you have an
Googling,
unbalanced data set, be cautionary, I guess, in terms of your approach and I guess how much predictive power the model really has.
yeah, there are strategies you can do though. There's like, you can upsample or downsample.
Right.
So I'm wary of upsampling, but I think downsampling is fine. And actually that's what I ended up doing for my dissertation work, where I had roughly 3,000 observations of charter school students and about 150,000 observations of, traditional public school students. So what I ended up doing is taking that 3,000 and then randomly selecting 3,000 traditional public school students, but just did that a bunch of times so I could maximize that that other group, and just ran a bunch of models and then averaged them across to kind of get, so that's considered downsampling, right? That bigger class, I'm just going to randomly select from that to get the proportion closer to my observed class. Upsampling would be,
You bag sample the
yeah,
you're
you're duplicating essentially your smaller class data, and that always feels a little. I don't have empirical data on this, but it just, given what I know how statistics works, feels a little like you're going to inevitably bias your estimates. But downsampling is great because you could do that in kind of almost like a bootstrapping approach. In fact, I wrote a package to do that for propensity score analysis that actually does that very strategy, where you create bootstrap samples across those groups to kind of equalize the classes. Things like classification trees sometimes are okay with more imbalance than logistic regression, for instance. So a lot of times my strategy here is just to try a bunch of different models and see, whether or not you get a convergence of conclusions or answers. And that usually bolsters my confidence in the overall approach.
Yeah, I guess if you have a large sample of your majority class, then downsampling is fine. I guess if you have less data, then that becomes a problem.
Yeah.
I mean, I guess, what do you think of techniques for numeric data, at least, with things like SMOT?
You mean, did you say small, like
SMOT,
smart?
that's a synthetic minority oversampling technique.
Oh, I don't know. I haven't thought about it, to be honest. Yeah, I think in terms of, I mean, a lot of the issues that I see in predictive models coming out of, say, Silicon Valley, which is predominantly white men, is, certainly problematic. And I guess, and the spirit of it sounds okay, but I haven't really explored it, so I really shouldn't say too much more than that.
Yeah, I mean, I saw in your, I think you had this, the ROC, that you had the weights parameter as well.
Yeah.
I think some of these models, you can also provide, if you do have an unbalanced data set and you have some good sense and intuitive feel for, how you want to steer the errors in the minority class, you can provide weights to these models that might, penalize bad guesses on the minority class a bit higher than bad guesses on the majority.
Sure, absolutely. Yeah, so yeah, he's talked about here, which there's these different costs. So you could specify costs for false positive, for false negatives, which will influence, well, in this, this cost curve where you're trying to determine the threshold. So that's, certainly a way to do it. And I think I might have talked about it before, but the only example I can think where you want to, where the type 2 error rate might be more important than the type 1 error rate is like an advertisement where, the cost of missing something is much greater than, putting it there. And basically the type 2 error rate is more expensive than the type 1 error rate. Given my social science background, I mean, it's really hard for me to think of examples that we emphasize type 1 error rates for a reason for however long, for the last century or so, since we've been doing these kinds of statistical tests. So there are other types of weights for sure. There is a package called Survey by Thomas Loonley that is largely designed to put weights in the models based upon usually sampling design, but I think it could be leveraged in other ways where, so in essence, what you want to do is with complex sampling designs, you often know the probability of somebody being in the sample. And so people who have a much lower chance of being in the sample, but are in the sample, you want to upweight them versus individuals who may have a higher chance of being in the sample. So you could leverage that package to do some of that. And of course, GLM and LM have a weights parameter, so you can specify that as well. But that's a great question. I'll have to poke around for some literature on that. All right, really switching gears. I should say the stuff tonight is not on the final exam, so you don't need to worry. These are sort of our attempt to give you a jump start to the rest of the program. And the next one is Bayesian analysis. And this is also to try to provide some context or some to reinforce what we've talked about this semester, which is largely a frequentist approach. And actually, I need to, I want to say this because I'm seeing some presentations. There might be still some confusion about the assumption of our regression model. So with LM and ordinary least squares, our assumption is not that our outcome or any of our variables are normally distributed. The assumption is that the residuals are normally distributed. I want to reinforce that. And so when we go to generalized linear models, we're still assuming some distribution of the residuals. Now, in terms of logistic regression, it's no longer normal, right? We're looking at we're looking at the logistic function, and we're looking at the logit as that distribution or the binomial distribution. So we're assuming the sort of the residuals follow the binomial distribution. If you have count data, you often use a Poisson distribution, right? So the generalized linear model, the generalized piece is saying, well, we're generalizing beyond the normal distribution to other distributions, but there's still an underlying assumption of that error distribution, okay? Not that the variables themselves are normal, but that error distribution follows a specified distribution. Okay, so that is the crux of frequentist statistics. It's that, and it's also this, the central limit theorem plays a key part of that, right? As our sample size increases, the sampling distribution is going to approximate the normal distribution, right? And so Bayesian is going to kind of take a different point of view. Oh, so we're looking at that. Okay, so first, I'm actually going to start with, because I would call myself a Bayesian newbie. I have very much been trained in the frequentist approach. I still use frequentist approach probably 95+% of the time, but I'm finding Bayesian approaches to be increasingly valuable in some of our work. Now, unfortunately, Angela and I, tend to work in educational social sciences, and Bayesian really hasn't made the headway into that world yet, but it's coming. In the data science world, I think it's very much accepted and used. Now, if you want to really dig in, so on the course website, we recommend Danielle's book, Navarro's book, because she has a chapter on Bayesian statistics, and it's free, open, you can read it, and I think it's a pretty decent introduction. Now, if you want to dig in deeper, this is the book I would recommend, John Kresge's Doing Bayesian Analysis. You can get it on Amazon. I think it's like $50 or $60, worth having on your bookshelf. The other thing I would recommend, if you're going to do some leisure reading over the break, is The Theory That Would Not Die. I actually love this book. It's more of a history book than a statistics book, but it kind of outlines the history of Bayesian statistics all the way back to Bayes' first writings in the late 1800s, and how it was used in different ways. The most famous, I think, use of Bayesian, the Bayes theorem and Bayesian statistics is probably Turing and his cracking of the Enigma machine, right? He used Bayesian methods to crack the German codes during World War II. And so anyways, this book goes into it. It's you can get it on Audible. I listened to it when I was on a long drive ride once. It was really fantastic. A lot of what I'm doing is adapted from a series of workshops I did with Rasmus Bath. I have a link to his 3 articles there. And then I'm going to show this. I don't want to talk too much about it to give away. But there's another article about billiards. We'll talk about billiards in a moment. All right. So Bayes' theorem, I think, was introduced in the probability chapter, whatever, months ago now. And this is kind of how it's stated, right? So we're trying to find the probability of A given B, where we have all these other components, right? We know the probability of B given A, probability of A, right, et cetera, and some complements. So let's consider an example here, and then we'll break down this formula. Actually, we're going to simplify it considerably in a moment, right? So we're looking at like the accuracy of breast cancer, right? And so we know from data that 1% of women have breast cancer. And so obviously the complement is that 99% do not. 80% of mammograms detect breast cancer when it is there, right? So obviously 20% don't, and 9.6% of mammograms detect breast cancer when it's not there, right? So we can kind of write this out in this 2x2 table. So then the question is, how accurate is the test, right? And so we need to consider all the scenarios. And so this is where, right, so what we're saying is we want to predict the probability of cancer given that the probability of a positive cancer test given there is cancer, right? But we have all these other components. And so that's the beauty of Bayes' theorem, right? So if we get a positive result, it means we're somewhere in this top row. Oops, there we go. And so we have the chance of a true positive is the chance you have cancer and the chance the test caught it, which is 1% times 80% or 0.08, right? And the chances of a false positive equals the chance you don't have cancer and it caught it anyways, right, which is the product of that. I don't know why my multiplication sign disappeared, right, which is the 0.09. So then, that result ends up being about 10.3. So when we think about how accurate a test, right, let's break it down. Right? What are we really talking about? Well, we're talking about the probability of the desired event being observed given all possibilities. So the chance of getting a real positive result is 0.08. The chance of getting any type of positive result is the chance of the true positive plus the false positive, which is about 0.1304, right? And so we can substitute that all in. So our chance of cancer, given this, is about 7.8%. If you got a positive test, the chance of it being actual cancer, 7.8. And this all is derived from Bayes' theorem. Now, right, so it's really about the true positive divided by any possible outcome. So we can simplify Bayes' formula down to this. And from a statistical point of view, or from a modeling point of view, what the shift here is, right? So from the frequentist approach, remember what we're doing and what the central limit theorem is saying. We're saying if we could have an infinite number of random samples, we know what that sampling distribution looks like. And we're going to make inferences from that sampling distribution. The Bayesian is going to say, the data is what I have. That's true. I'm not going to assume anything about any sampling distribution. All I know is what's true. And so I want to see how often I could observe that given that data. So you can think of this as the probability of some outcome given my data. Right. And so this is from Chris Albin. I think I like this description, right? So we have, right, so we're going to be looking for some posterior distribution, right? We have some likelihood, and we have a prior, and we have the marginal likelihood. So let's break that down. And I'm going to do it through an example, and through an example that turns out to be extremely hard to solve from a frequentist point of view. But so if we want to estimate the population of fish in a lake, kind of a silly example, right? What could we do? We could try to catch them all. That's not really practical to count them. So we want to use some kind of sampling procedure. All right, it's a smaller pond, right? So I'm going to go out in my boat. I'm going to catch some fish. And then I'm going to mark them, and I'm going to put them back into the pond. And then I'm going to allow enough time for them to shuffle so I can go out and randomly select some more fish again and count how many of them were marked, meaning they were caught 2 times. That's the only data I have. And from that data, I want to get an estimate of how many fish are in the pond. Now, specifically what we did is we caught 20 fish, we marked them, and when we went back out, 5 of them were marked. So we caught 5 fish twice. And that's what we have. So that's what we want to do to try to figure out how many fish are in the pond. So when you start with a Bayesian procedure, you want to start with some prior, right? And this is often where Bayesians get criticized is by using this prior, or that you could specify a prior, but we'll see that it's somewhat robust to bad estimates. But if I don't know anything, right, I'm not a fisherman, I'm not an ecologist, so I have no prior knowledge. So I'm just going to say the likelihood of there being there has to be at least 20. So I have a floor of 20. And clearly it's a small pond, so there can't be more than 250. So I just have to put a bounds here. So my prior is just going to be a uniform distribution. So what I'm going to do is say the likelihood of there being 20 fish and 250 fish is the same as 100 fish is 150, right? All the way across the range. So sometimes it's called a naive prior. It's also a uniform, prior. So what am I going to do? I'm going to actually do some data simulation. So I'm going to say, I'm going to do, what did I make that? 100,000. So I'm going to do a simulation 100,000 times. And what I'm going to do is now I'm going to sample from 20 to 250, right? And you can see here's the head. So I have, this vector n fish that's equal to 100,000. We can see it's uniform. What I'm actually going to do is I'm going to run some simulation where I'm going to guess there's 117 fish. And then I'm going to guess there's 108 fish, 136, all the way through all 130 observations to see what I get. To do that, I have to define some kind of generative model, right? Or a way of generating fake, quote unquote, fake data. So what am I going to do? So I'm writing this simple little function here. that takes as a parameter the number of fish. That number of fish parameter is actually going to come from this vector in a moment, right? So let's just say it's 100, okay? So what I'm going to do is repeat 0, 1. So 100 minus 20 because I have that floor, and I'm going to do it 20 times. So, well, and I'm sorry, I'm going to repeat, 0, in this case, 80 times, and then I'm going to have 20 ones. Okay. And so I get that fish, and then I'm just going to randomly sample 20. Why 20? Because that's what I had at the beginning, right? That's what I got when I went out on my boat, right here. Okay. Oops. And so from that, right? So I can do that. Oops, where's my generative function? Okay. So let's okay, so I'm going to initialize this other vector called n marked with missing values, NA, and draw, which I think was 100,000. Yes. Now I'm just going to loop through all of them, call pick fish with that vector, right? So I'm going to call pick fish with 117, then 108, 136, right? So this is all just generated randomly. And if I look at the first 10 rows, right? So with 117, I'm sorry, I ended up with 6 marked. I guessed 108, 3 of them were marked on the second pick. Then I did 136 and I got 5, right? But so I got a whole bunch of values. So now I have this vector of 100,000. So what I'm going to do is I'm going to keep all the ones that are equal to 5, because that's actually what I observed, right? When I went out on my boat, I caught 5 fish twice. So I'm going to keep those, and I'm just going to plot the histogram. So we call this the posterior distribution. So these are all the number of fishes that resulted in what I actually observed. Okay. And I drew a red line here. So the median is somewhere around 100. And I did a 50% kind of confidence interval or here. So I'm 50% sure there's somewhere between like 75 and say 125 fish, right? So I just did this all randomly. I had this one observation. I wrote this generative function and I generated it. Right. And so these are all, this is the distribution of outcomes that would fit what I actually saw. All right. But I have some expert, fisherman who's on the pond and goes, I think there's around 200 fish in the in this pond. So I want to leverage that, right? This is an expert. He might know something about this. So instead of using a uniform prior, I could use a binomial prior, right? So that's what I did here. So I used so I'm using the random number from the binomial distribution. I want 100,000 of them. I'm going to use 200. I'm going to subtract that 20 because of the floor effect. And then I'm going to add the 20 back out over here. Right. And so here's a prior distribution. So this is my new N fish. And so this part is exactly the same. And I'm going to keep the 5. And now here's my posterior distribution. So given that prior distribution, I have a different posterior. Note that, right, in my uniform, I would have guessed 100. This one here has a little bit higher, but it certainly doesn't enclose 200. So this so-called expert really isn't an expert. And arguably, this is a bad prior, right? Because there can't possibly be 200 fish in the pond. But the model still kind of came out, was kind of somewhat robust to it. So, so the frequentists say, well, you can bias your estimates by just specifying these kinds of priors, which in some contexts may be true. But the Bayesian would argue and say, well, why would I run a study or a test and ignore all the prior research that I have in estimating my my confidence intervals, right? And so there's kind of this balance, right? And the frequentist is saying, well, there's the central limit theorem tells me that there's some theoretical sampling distribution, and I'm going to make my inferences from this theory. And the Bayesian says, but all I know is I have my data. So let's simulate data and see how often I get what I actually see, right? Do you see this contrast between these two different approaches to trying to solve these models? So I love this example. So Bayes, when the first paper he wrote on Bayesian in the late 1800s, and this is a time, I think before statistics was it was just starting to become formalized as a discipline. And early statisticians always wrote about games, and they often invented games to try to understand probability problems. And so in this game, Bayes said, well, imagine we have a pool table and we're going to call it length 1. We're just going to say it has a length 1 for simplicity's sake. I'm going to throw the black 8 ball, all right, and I'm going to mark its location. And then I'm going to throw subsequent balls, and all I'm going to tell you is the ball landed to the left of the 8 ball or to the right of the 8 ball. And your goal is to tell me where the 8 ball is without seeing it. Okay. So I wrote a little Shiny app to kind of do this because I thought this is such a cool little problem and quirky. And so here, right. So I can specify a confidence range. So what I did is I started in iteration 1, I started with the uniform distribution. You can change it to a histogram just to see that it is indeed uniform. Again, I think I mentioned this about you got to be careful with density distributions when you have sort of hard floors or ceilings that it kind of tails off. All right. And so in the first iteration, I said the first ball landed. I think this is backwards to the right of the 8 ball. Okay, yeah, right. No, that's right. So the first ball landed to the right. So I took all those guesses, and what I essentially did behind the scenes is randomly drew a number. So I would say, well, my input is let's look at 0.25. I randomly draw a number between 0 and 1. And if it's greater than 0.25, I would say I would agree. And then otherwise it would be false. So this ends up being my posterior distribution. So hopefully intuitively, right? We only have one observation. All we know is the 8 ball is to the right of what I'm sorry, the ball landed to the right of the 8 ball, right? So it makes sense that we're probably leaning towards the 8 ball being to the left side of the pool table. Does that hopefully intuitively make sense? Okay, so let's do it again. All right, so on the next throw, the second ball also landed to the right. But now I'm not going to start from scratch. What I'm going to do is I'm going to take my posterior from iteration 1. That's going to be my prior in iteration 2. And then I'm going to run that same thing. So after the first run, right, this is where I think the 8 ball is. Now after iteration 2, I'm going to squeeze a little bit more to the left. And, my confidence interval is going to, confidence range is going to shrink a little bit. Well, we can do it again, right? Landed to the right again. So I take the posterior, from iteration 2 becomes my prior in iteration 3, run through my generative function, and now I think the 8 ball is here. So maybe let's go, there's 4 to the right again. Now on the 5th iteration, it ended up on the left. So on that last iteration, I took the posterior from iteration 4, became my prior in iteration 5, and now I have this posterior, right? And this is kind of where I think it is. And where is it? And we can go and look and say, well, we can see where the answer is. So now we can kind of see where those guesses are, right? So here's iteration 1, 2, 3, 4, that 5, right? And you can see here in this vertical line, I kind of captured it almost right away, right? And so that's where the 8 ball is. So we're using that information as we kind of go through, but the key part is we're kind of like generating data to see what our randomly sampled data or randomly generated data matches the data we actually observe and see. And that's sort of a key concept for the Bayesian approach. Questions?
I have a quick question. So
Yeah.
just using like the formal definition language. So like if you go back to the Shiny app, so your evidence in this case is where you're observing your ball being thrown, and your hypothesis is where you're trying to guess the 8 ball is located.
Yeah, we're trying to locate it. Yeah.
Okay. And so you're updating that guess, you're updating your hypothesis as you have new evidence where you're seeing more and more balls.
That's exactly right.
My question is, doesn't this kind of reflect a frequentist approach? and that you're generating new, I mean, I think wouldn't like, I guess another way of asking is like, would those confidence intervals, or maybe like the overlap of those confidence intervals, converge if you just ran the simulation enough?
Yeah, you're going to get smaller and smaller, confidence ranges, for sure. It is, so I can see where you can see that. So this, and this is, I'm going to be honest, I'm on this path, with you, and it's taking me a while. So the bootstrapping was sort of my introduction, or sort of my gateway to Bayesianism, because what I really love about the bootstrap, right, is you're just randomly selecting from your data, right, with replacement, and you're not assuming really that the bootstrap distribution is going to be normal. Now, it always turns out to be, because the central limit theorem is a theorem, right? It is, as you do more samples and as your sample size increases, that bootstrap sample should also be normal. But I can actually see that distribution, whereas the sampling distribution from traditional frequentist approach, I don't see. I just know it's normal, and we kind of go with it. So if you look here, like these posterior distributions are not normal. They're very skewed. So in some ways, yes, but there's none of this assumption about normality. There's nothing, this notion of that distribution at the end is going to have any kind of shape. It's going to have the shape it's going to have. And I'm just going to read the confidence, the confidence range from that, right? So kind of, but if insofar it's like close to the bootstrap, but it's a little bit different. Does that help?
Yeah, I think that makes sense.
So as you could, probably it might be obvious here,
So
I'm sorry, go ahead. No, you go ahead.
Essentially, with the frequentist approach, you're not updating
No.
of the distribution with each iteration.
Right. The Bayesian would say, why? So we do a null hypothesis. The frequentist always assumes the null. We're always starting from ground zero. And the Bayesian says, but we have a lot of research that suggests that the null isn't right. Maybe we should start where all the other research says, right? So the frequentists never really update. They're always starting with the null. And what I was just going to say real quick, the sort of increased popularity of Bayesian is sort of directly related to the availability of high-powered computers, because I think why some of this didn't, the reason why Alan Turing used it, because he recognized very quickly that the Germans were changing their codes every day, and he couldn't possibly try every combination. So he learned patterns in how the Germans changed their code to reduce the number of codes to try, right? And so that was key for him to be able to do that. And that's key for a lot of problems. Like if you read that, the theory that would not die, there's some interesting, and during the Cold War, there was a lost nuclear missile from a submarine, and how they used Bayesian to create search grids and update the search grids after they got results from each one in order to narrow down where it was. There's all sorts of interesting applications of this. Of course, there are now sort of direct analogs. So you can just Google like Bayesian logistic regression. So if you're doing logistic regression, you want to solve it the Bayesian approach, right? So we learned, so logistic regression through the GLM is going to use the maximum likelihood, but you can solve that kind of model using a Bayesian approach where you have your data and you're going to try different estimates and see how often you observe the data you get for that particular estimate, right? So it's just kind of solving it with a different process. And you can do that using naive procedures. So naive Bayes methods would just sort of essentially just use a uniform distribution, or you can specify your priors. And if you really want to go down this, there's like sort of special languages like JAGs and I can't remember the other one, but you can interface through R and I think through Python too, to help you, define generative functions in a language and then run them through. Other questions?
So just in terms of how you're plotting the distribution below, so are you plotting the range? I guess like, are you running that like simple, like conditional probability equation and then like seeing what the distribution of the value is in terms of generating that?
Did I put it in the about tab? So I kind of run it through here. So, yeah, so I started with 5,000. So one thing, you might notice is that they don't look exactly the same. So because what happens is, I think I started with, I forgot already. How many did I start with? Oh, I think it's a parameter. Shoot, I keep going to the wrong thing. So 5,000. I can go
Okay.
to 10,000, right? So so you could tell, like, each time I click the next, it takes a bit. If you see that flash, if I go to 10,000, it's going to probably take twice as long. Okay, so here I end up with I have 10,000 observations here. So when I look at the posterior, I have fewer than 10,000 because I'm only keeping the ones that I have. So what I do to go to here is I sample from this distribution to kind of upsample it. So these little like dips are sort of just random noise. And as I go from here, this one here, you could see maybe a little bit more. It's not exactly the same distribution, because what I want to do is I want to start the prior with 10,000. So I'm sampling 10,000 from this smaller sample to make it look like it's almost the same.
Okay.
So that's one little trick there. I'm not sure if that was exactly your question, but if you go through this, the about page, kind of runs through it. So you can see, if I start with 5,000, my I'm using the random remember our distribution functions in R. I'm using the uniform, the R is for random. So we can see I have a uniform, prior. So then, I can't remember what prior distribution currency. Okay. Okay, so we're saying the ball landed to the left, I think. The 8 ball's to the right. So the ball landed to the left of the 8 ball. So what I do is, from my prior, I'm going to randomly uniform again another 5,000, and I'm keeping only the ones that are greater than the prior, right? Because that's saying, well, the 8 ball landed higher than that. And so that becomes my posterior distribution. Then, so you could see what I'm doing is I'm sampling from my posterior 5,000 times with replacement to get a new prior, right? Because
That's
this
why it doesn't include
posterior,
that distribution. Okay.
yes,
Gotcha.
because this posterior is going to be less than 5,000, but I want to start each iteration with 5,000.
Okay.
And this is how I do it.
That makes sense. Okay.
Right. And you can keep going through. And I think, oh, I'm sorry, it was 1763. Is that oh, it's not there now. I have to update that reference. I bet you if I just search with Google. Maybe. Yeah, it just tells you how old it is. Look at the is there a year on this? Yeah, 1763. I was off by a century. Sorry about that. Other questions?
Professor, can you go back to that Shiny app?
Yeah, absolutely.
If you will.
Oh, by the way, if you want to play around with it, I thought Yeah, and then I'll put this, it'll be in the slide deck when it gets posted, but here's the blog post I wrote about it a while ago. But go, yeah, question?
So we're trying to predict with this where the cue ball, where the 8 ball will be. But let's say the 8 ball was directly in the middle, then the probability of each ball you randomly throw will be on the left or right equally, right?
Yeah, yeah.
What would the distribution?
Here,
look-
let's see. We can start over. Let's
Wouldn't that also affect the distribution on the
yeah,
top?
absolutely. It'll probably look more normal. I'm trying
Right.
to the random number, that's close enough, right? So we're 0.43. So let's just you see we got left, left, right, right, left, left, right, right. I swear this is random. If you see patterns, it's just a coincidence. So now we're kind of skewing right to the right. So actually, you're going to find it faster on the margins, it seems. But it'll come back.
What does the distribution look like?
Yeah, they're all starting to normalize, right? So really, the you can think of it as like the highest point should start being around where the 8 ball is. So if the 8 ball is is on the left side of the table, right? We saw the distributions were skewed over here. If it's on the right side, the distribution should tend to skew to the right. If it's in the middle, they're going to start to look a little bit more normal. And we can see the zigzag, right? So here, when you show the answer, when you say show the pool table, I also put this vertical line as you go through. So here, but you can also see each iteration as you go through.
How similar is this to a binary search?
Oh, no, I mean, a binary search is just an algorithm to search through usually a tree structure.
Correct. Yeah.
Yeah.
I mean, it seems somehow similar to that. I mean, just at obviously very different algorithms and very different approaches, but it seems that you're searching through a space, right? Your search space in this case happens to be, 1,000 samples.
Mhm.
And at each iteration, like in this particular example of finding the billiards ball, you're saying left or right. It's really cutting down the search space almost by half, it seems. It should.
Yeah. No, I see where you're coming from, Jawad, but not quite, because in a binary search, you're gonna reach a terminal node and actually get the solution. This might be more akin to, I mean, this in some ways is kind of related if you're coming from a computer science background, like greedy algorithms. So things like Dijkstra's algorithm, I don't know how many people are from computer science, but like when you do driving directions, so you can Google Dijkstra's algorithm, and that's typically how they all do it, because you can't possibly search all possible paths between point A and point B. And so there's this notion of greedy algorithms where it's greedy because it makes decisions to the end based upon optimizations at the local point, right? You make a lot of local optimized decisions, but you leave room to kind of back up and kind of go a different path if you end up with a more optimal solution. So that's so there's a whole class of things called greedy algorithms. So in some ways, Bayesian is kind of very similar to that, in that we're making assumptions based upon the most recent bit of data we have as we traverse down. In this case, it's left or right. I could see why you end up in the binary because we're just looking at two outcomes, but we could be estimating anything this way. Estimating something to left and right, I think, just in terms of trying to explain and understand the concepts is helpful.
Got it.
Does that make sense? Does that help?
Yeah, it does. Would it be more similar to then gradient descent? And I'm just going off by what you said about making local.
Yeah.
Decisions, yeah.
Yeah, I mean, it's kind of similar in approach, that you're which is why I spend so much time on the sort of maximum likelihood estimation, because even that's in the frequentist kind of realm, but that shift from sort of algebraic solutions to algorithmic solutions is sort of a key piece of what makes so many predictive models really kind of effective and different. And when you get into other, so this is Bayesian, then there are other like non-parametric methods. So non-parametric, right? So remember, I think it's worth repeating, parametric and frequentist approach. And the parametric is saying that there is an assumed distribution of our error terms. And the non-parametric says, well, there's no assumption of that error distribution. It can be whatever it is. So things like classification trees or regression trees kind of fit that bill. Random forest, if you think about that, that's a non-parametric method. Bayesian is kind of non-parametric. You kind of relax those assumptions and that algorithmic approach allows you to see things that aren't there, or that would be harder to detect, sort of using just ordinary least squares or even just maximum likelihood. But I gotta say, maximum likelihood estimations are still the backbone of a lot of data science. You're gonna want to learn all these fancy things, and which you should. They're great, but logistic regression is still up there, I think, performing with the new latest greatest things in terms of performance, in my experience at least. Some people like it because logistic regression is so well known, and it's pretty easy to interpret. You get into neural networks, I see people doing studies and dissertations on trying to understand the output of neural networks. Like there's so much going on in there and how it makes decisions that we don't understand, which is just kind of crazy. And even random forest, which the procedure to do it, right? So what random forest does is you're trying to, well, let me just say real quick, and as with classification trees, what you're going to do is you're going to take your data set, and I'm going to try to see on what variable. I'm going to look at all the variables, and I'm going to try to split the data into two that maximizes the difference in my outcome in those two groups. And then it just does that iteratively. So I go down the left, I'm going to take that subset of data and then try to split it again on any of the variables. And I do that repeatedly until I can't split anymore, right? So it's very algorithmic. Random forest says, I'm going to randomly select some data, and I'm going to randomly select variables at each of those nodes, if you will, as you split down a tree, right? And so, that's great, right? Kind of in my 1 minute explanation, you hopefully get a sense of how it works, but then how do you know what variables are important in your model? And so, there's things like random forest explainer. Oops, I spelled that wrong. Right. So there's a whole R package designed to understand the output of random forest, and you get these kinds of plots because it's not like there's no estimate, right? When we get a regression, we get an estimate, we have a t statistic, and we have a p-value with it. We know whether or not it's significantly related to our outcome. With these other kinds of more advanced models, it gets a little bit harder to know. Now, for a lot of data scientists, they don't care. How accurate is my new predictions, right? We're going to look at that confusion matrix, and it's this accurate. I don't care how I got there. And so if that's the case, great. These kinds of procedures are great. I'm still a little old school in that I kind of want to know how my independent variables are related to my dependent variables, which ones are more important than others. And so anyways, like I said, this is all jumping ahead, and I wish I could teach more courses in the program because I love this kind of stuff, but I'm trying to set you guys up for success. I'll throw this link in if you want to read it.
Sure, thanks.
Other questions?
I have a few off-topic questions,
Sure. Go
more
for
like
it.
personal questions.
Oh, do you want to wait till I turn the recording off and all that?
Yeah, sure.
Great. Any other questions about Bayesian? Sorry, we went so over. Next week we'll keep it short. All right. Then let's call it a night. We'll see you guys next week. Some of you will see Friday or next Tuesday for presentations. The ones that have gone have been great so far. So looking forward to it.
Professor, last question about the final. Which chapters will it be on? Maybe we already discussed.
Just topics kind of in the open intro book.
The entire open intro.
Yes. Let me look at the emphasizing the second half since the midterm.
Fair enough. Thank you. Thank you.
Open
Professor.
book, open notes, whatever. Just don't consult with anyone else.
Understood.
That's fine.
Thank you, professors.
Yeah.
Good night.
Good night.
Professor, I have sent you a message through